So we're going to go over this example one, and what I'm going to have here, this is sort of the key here. Anything blue, that's going to be the instruction which we just executed. So when you see an instruction listed in blue in the next slides, that means I just executed that. And then if you see something in red, that means, as a consequence of that instruction, we just modified some value. And then the stuff in green is just some arbitrary starting value which I've chosen. So this is just filling in registers, etc. I think I gave them roughly realistic values based on what I saw when we did this, when I did this in Visual Studio. But to explain what we're going to be seeing here, for instance, this right here, this 4012E8, we're going to consider this to be, so we're going to start right with this push in main. We're going to pretend again that main is the first, well, okay, here we're not pretending that. We're saying there is something out of scope, some initialization code which gets run before main. And now that initialization code has just called main. I'm sorry. Ariel, can you close that door for me? So we said there's going to be some initialization code which executes immediately before main. And when that code does the instruction call main, that call main is going to put a saved return address onto the stack, right? And so this initial value, which I'm pointing out here, this is just the address after the call in whatever initialization code ran before main, but it's like outside of the scope. I'm just trying to point out here, this is something which will be on the stack, at the top of the stack, right at the very first instruction of main, right? Whoever called main, the saved return address is going to be there on the stack. All right, so now we're going to start it out. And we're going to say our first instruction that we're going to execute, we're going to start at main. Main was just called. We're going to execute the instruction push EBP. All right, and so what's that going to do? By initialization, we said that we had the value 12FFB8. That was the EBP when this code started executing. And that was pointing at the frame of the initialization code which called main. So that was some frame which is out of context. We can't see it on our picture here. Happened before our code was called. But once our code is called, main, it pushes EBP as the first thing. And Amy, this gets to the convention. The compiler just automatically generates these first two instructions, this push EBP, move ESP to EBP, push EBP, move ESP to EBP. These two instructions are automatically added by the compiler, basically. And this reminds me, well, I'll get to it in the next instruction. Anyways, so we had 12FFB8 sitting here in the EBP register. We did push EBP. And therefore now we put 12FFB8 onto the stack, right? And also we see the modification to ESP right here. So we see a modified ESP because, right, when the push instruction is called, ESP always needs to keep pointing at whatever's on the top of the stack. The thing that's on the top of the stack now is this 12FFB8 that we just pushed. So ESP gets 4 subtracted from it. So going back to the previous slide, we said by initialization, 12FF6C was the stack pointer, right? So stack pointer was pointing at this green stuff. That was our top of our stack right before we executed the push EBP instruction. And when we execute the push EBP instruction, it gets subtracted by 4 because we just put something on the stack. Stack grows towards lower addresses, right? So subtracting when we add something to the stack. All right, so that was our first instruction. The only things that got modified is something got put on the stack and the stack pointer got moved down so that it stays pointing at the top of the stack. Moving on to the next instruction. Now, the thing which I neglected to put here and which I had put in my notes before and which I still hadn't fixed is on the Intel syntax instructions, which we're going to be looking at in the beginning part of our class for the Windows stuff. The source, well, so the destination is the thing on the left. So Bill, over at the whiteboard. So if we have any instruction, so any given instruction, this will be the destination on this side, and this will be the source over here. And for instructions where it takes 2 parameters, so like if this was a move instruction, right? This would be dest, and this would be source, and this could be, say, EAX and then maybe EBX. right? So what this is just saying is take EBX register value, whatever's in EBX, and put it into EAX. And so that's what we're seeing right here. We're seeing move ESP to EBP, right? ESP to EBP. Take this and put it into that. That's all we're doing. Now, the reason I call this out and why I should have called this out in the slides is because when we get later on in the class, AT&T syntax, which is used on like Linux systems, it's the exact opposite of that. So you switch the things around. So that'll get a bit confusing then. But for now, it's just put the thing from the right into the left. I think of this like, you know, algebraic equations and stuff like that, right? So you're used to doing like, you know, y equals x squared plus c or something like that, right? And the destination is over here on the left. And so when we switch it around, it'll be the opposite. But the other thing I want to say about this instruction form is that if we have something which takes two things, so we haven't covered add yet, right? But I think you'll have a good idea of what add does. If we did something like add EAX and EBX, then what this does, you know, it's still destination and source, but actually the destination is also used as one of the operands. So therefore, this would do EA. All right, so if you have something like an add instruction, this would do like EAX equals EAX plus EBX, right? So you just do this plus this and put it still into that destination thing on the left side. So that's all I want to say about, you know, instructions which have two operands. You need to have the destination on the left. So now we get to this move ESP to EBP instruction. And so for this one, basically, you take whatever was in ESP, right, 12FF68, and you put it into EBP. And so that's why you have a modified value right here, 12FF68. You just put that into there. And this is basically the instruction which is setting up the new stack frame for main. It's saying, right now I want EBP to point at 12FF68, and therefore everything from 12FF68 and below, I'm going to consider that part of my stack frame. All right. Next instruction. This is our call instruction. And so it's saying call sub, and sub is this function up here at the top. And so what it's really saying is, you know, call to the address 401000, because that's the address of the first instruction of sub, right? 401000 right here. So it's saying, I want you to change the instruction pointer and go to the subroutine. And so what's going to change here? As a consequence of this, right, I said the call as sort of an implicit thing in the background, it's going to be pushing the address of the next instruction, right? And so what's the address of the next instruction? It's 401018, right? That's the instruction which is immediately after the call instruction. And so that's why we see this 401018 sitting here on the stack. Question?
I have a question. This may be silly, but are these addresses determined at compile time or at runtime?
No. So his question for those on the phone was, are these addresses determined at compile time or runtime? And so they are runtime, and they're generally speaking created by convention on the operating system. So the operating system will say, well, actually, let me put that a different way. They are set at compile time in some sense, because at compile time, the linker will put into the binary, and this will be something we cover in Life of Binaries. At compile time, it'll say, here's my preferred virtual address where I want to start my, load all of my code starting at this address. And that'll be somewhere inside the headers for the binary. It'll say, start me at this address, and then, all of my code will be relative to that. So in this case, maybe the binary said, start me at 40. Well, typically by convention on Windows executables, it'll be 40 0000. So that's implying that this subroutine is like actually hex 1000 into where this thing would have been started. So in that sense, it's set at compile time. In another sense, when you deal with things like libraries, DLLs and stuff like that, those can be moved around in memory, and also you may be aware of address space layout randomization and stuff like that in newer operating systems. And what those do is they just say, okay, well, I know you want to be loaded at this address, but you don't necessarily get to be. So I'm going to move you around to help prevent exploits or whatever. And therefore, in that sense, they're set at runtime. So an executable may have a preferred value that it wants to start there, but the loader, the OS loader, can still just say, well, I'm going to put you somewhere else, and you're going to have to fix yourself up. And these addresses can be completely different. And it's also, runtime in that sense, because the operating system will have different conventions for where they start stuff. So when we get to Linux things, you'll see things more like 0, 8, something, 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 and that'll be the default for executables, as opposed to 004, something, something, something.
So in other words, in many cases, these may be predictable, but you can't count on it.
Right. So in some cases, these will be predictable, but you shouldn't ideally, you should never hard code addresses like this. You'd never want to hard code something like a 401018 into some other code which is trying to jump there or something like that, because these things can move around. Executables, at least in Windows XP, for instance, the executable is always guaranteed to get its preferred thing, but then the DLLs are not guaranteed, so those can move all over the place. So I don't believe that's the case, though, when we start getting into Vista and things with address space layout randomization. And then, but for things like Linux, if they don't have address space layout randomization, and then you could potentially say that it is predictable for the executable, but not the libraries and stuff like that. So you could say that is deterministic. But yeah. All right. So, anyways, we said here we just executed the call instruction. And what it's going to do is it's going to change the instruction pointer. So like I said, thus far we've just been going blue and then move down, blue and then move down, blue and then move down, right? And the point of the call instruction is no longer are we just going to immediately go to that next move instruction, right? We're going to go to the subroutine. And that's at the location 401000. So we're going to go to this push instruction next. So going to the next slide. Here we are. We landed at this 401000, and now when that instruction executes, it's going to again do push EBP. So our EBP was 12FF68, so that was pointing at the stack frame for the main, and now we're going to push that, save that copy of that stack frame onto the stack, and so that's why we see right here in red 12FF68. Simultaneously, we also saw the stack pointer moved, right? So ESP got moved down to match where that data got put. The data got put at 12FF60. So ESP just, again, decremented by 4. That's why ESP is red, and EBP is copied onto the stack here, and that's why the stack location is red. All right, now we move down to the next instruction. Again, this is just a standard function prologue kind of thing. It takes ESP and it moves it into EBP. So we had ESP right here was 12FF60, and then we moved it into the EBP register. So now the EBP is also 12FF60, and that's basically saying now sub is trying to set up its own stack frame, right? So sub stack frame starts at 12FF60. So we've kind of, well, I think it's, are we at, yeah. So the next slide kind of talks about stack frames, and this is like the extreme minimalist case kind of here, in that sub will have a stack frame that starts right here, and it can keep adding stuff. If it had local variables, it would maybe put local variables below this. If it had to do call save, or if it was going to call some other function, it would put it below this. But for all intents and purposes, sub's stack frame is only ever going to have the saved copy of the previous stack frame, right, in order to maintain that linked list kind of thing that we showed before. So at this point in the code, right after we executed this move ESP to EBP, sub stack frame is right here because EBP is currently pointing at 12FF60. Mains frame is right here, 12FF68, because we can see if we look at our current EBP, which is pointing right here. We take the value out of memory right there. That's a pointer to the previous stack frame. So this points to the previous one, 12FF68, and then this one points to the previous one as well, 12FFB8. That's, you know, somewhere outside of our picture, but that's the sort of linked list that we're dealing with here. So that one points to that one points somewhere outside of our picture. And above each of those stack frames, right, we see the saved instruction pointer that was pushed by a call instruction. So here's the link, and right above it, 401018. That's some saved instruction that's going to be immediately after some call instruction. And again, right above this stack frame, right above main stack frame, again, there's 4012E8, which we're just saying by convention or by assumption that was the address after whoever called main in the first place. So this is kind of just the stack frame timeout. Do we have any questions thus far on, you know, what we've done to get into subroutine, why its stack frame looks like this, what the components are of the stack frame, anything like that? Anyone on the phone? Any questions about stack frames where we are right now? How fast does this move? Oh, yeah, I gotta move my mouse. I'll try to move my mouse a little slower since I can see it doesn't track very fast on the remote video. All right, well, we're going to continue on because now we're going to get to this moving hex beef to EAX. So if you remember the original C code, right, I'll go back to that. Right, here's our original C code once again. We said subroutine, the only thing it does is it returns hex beef. And so if we say that by convention the EAX register is what you do, where you place your return values, then we would expect this C code to basically take hex beef and stick it into the EAX register, right? So going back forward, that's exactly what we see here is hex beef is moved into the EAX register because by convention that's where you're going to stick your return value. So we did that, and the only thing that changed here was that our EAX up here was initialized to hex beef, 32-bit value. And nothing changed on the stack here. But now so this was like the only instruction of actual functionality for this thing. All the code above it in sub is compiler generated automatic set up a stack frame. All the code below it is tear down a stack frame and return to the previous caller. So we did our single line of actual work. Oh, yes, question?
So is it possible to return more than one value? Because you can't put it on the stack without messing up your...
Right, so the question was, can you return more than one value? And so typically speaking, not in, you know, registers, for instance, right? So by convention, you can put stuff only in this one register. And typically what programmers, I mean, this is even back to C, right? In your C program, in C++, you may be able to return an object, and that's kind of like returning multiple things, right? But really, in your C program, you only return one thing, right? You define this function returns an int, this function returns a, you know, whatever, Boolean or something like that, right? So it's a limitation more on C, and then that exhibits itself here in the assembly. So when you return multiple values, you typically do that by, you know, passing by reference, right? You pass in a pointer, and then the code within modifies the data that points to, you know, that pointer points to, and in that way, then, you know, the function which called you and passed in that pointer, it can still see the modified data, right? So typically, if you return multiple things, you're just going to pass by reference and modify data at pointers, things like that. All right, so now we did our one line of actual work, and we're going to now tear down our stack frame. So we're going to do pop EBP. So we took what was stored here at the stack pointer. So the stack pointer was pointing at 12FF60. And now we popped out that value. So the stack pointer, when we do a pop, we add 4 to it so that, you know, we get rid of that value on the stack. So now stack pointer, it points at 12FF64, right? So the top of the stack, is now this value right here. And that value which was in this place, which I'm now marking as undefined, we did a pop EBP instruction, right? So that's saying take whatever's on the top of the stack, put it into the EBP register. And that's why EBP now is 12FF68. That was in the previous slide. That was what was there. And so when we pop it into the register, that's where it goes, and we get it off the stack, basically. Next, we're going to do the return instruction. And I said there's two forms of return instruction. Either it'll just be a plain return, or it'll be a return with some constant after it. And if there's a constant, it means like take that much extra off the stack. But we're just looking at a plain return right now, right? So for the plain return, all it does is it says whatever is on the top of the stack when this instruction is executed, go ahead and take that off of the stack, and I'm going to put that into the instruction pointer, and that's where we're going to go back to next, right? So what was on the stack? 401018, right? That was at the top of the stack. Stack pointer was pointing at 12FF64. So take whatever's at the top of the stack, and that's where we're going to go next, right? So what instruction, this is where we're at right now. We just executed the return instruction. Which instruction are we going to see next? Which move? We got lots of moves. Louder. I can't hear you. Yes, move food into EAX, right? Because that's at the address 401018, that's where we're going next. Yes?
Is there any effective difference between return and pop ESP?
Well, if you did, so the question was, is there any difference between return and pop ESP? The difference is, if you do pop ESP, you take whatever's at the top of the stack and you put it into the stack pointer, right? So you put it into the ESP register, right? When you're doing return, it's actually taking whatever's at the top of the stack and putting it into the EIP register. And so I said before, we can't do like a move directly. We can't use like a move instruction to set the EIP. We can only use these other implicit methods. Call instruction sets the EIP. Return instruction sets the EIP. These are the ways that we can do it. If we use a pop, we only end up setting the ESP, for instance, or some other register. So when we did the return instruction, it popped the thing off the stack into the EIP register. And because it's, kind of implicitly a pop, we again add 4 to the stack pointer, move it up to 12FF68. That's why you see ESP is 12FF68, right? And so now, as expected, we go down to the move hex food to EAX, right? And so the only thing that we see changing in this slide is that EAX gets set, right? So EAX was hex beef, and then this instruction just goes ahead and overwrites it immediately because our original C code just did return hex food, right? If we wanted to modify this, right, if we wanted the original function to return hex beef instead of hex food, we could just like put nothing after the call to the subroutine, and then implicitly the EAX from sub would still be set to beef when we return from main, right? So EAX is the return register, and that would still be set to beef, but in this case we immediately overrode it, functionally nullifying any effect that subroutine would have had, and then we just returned food anyways. So in this case, EAX got set. Now we move to the next thing. This is again just tearing down, we're starting to tear down the stack and return to the previous function. So pop EBP, we took whatever was at ESP, right? So ESP pointed at 12FF68 in the previous slide. And we said ESP pointed at 12FF68, and now we're going to execute pop EBP that says whatever's at 12FF68, pop it into the EBP register. So take it off the stack, put it into EBP, and then move the stack pointer up by 4 so that it's no longer on the stack essentially. So we see EBP got changed. That just restored that frame pointer for the frame of whoever called main. That frame pointer gets reset back there. That's somewhere outside of our scope, outside of our picture. And then we move the stack pointer up again so that now the stack pointer, right before we do the next return instruction, the stack pointer is again pointing at this assumed return address which was saved by the call main. So now we execute the return instruction. Again, the return is like an implicit pop into EIP. And so we take whatever was at the top of the stack, which was 4012E8, put it in EIP, and then move the stack pointer up by 4. So 12FF70 is outside of our picture, but we've just moved it up by 4 so that now everything's undefined. We consider everything below the stack pointer numerically as undefined. So, any questions on this example that we went through right now? So, we'll be going through one more like this where we do, every instruction at a time, and it'll be more complicated. We'll be passing values, etc. But any questions on the instructions we saw in this thus far? People on the phone? Questions? Alrighty. So, just some miscellaneous notes about this. Subroutine, like I said, is functionally dead code. It's not doing anything because the only thing it does is put a value into EAX, right? Puts hex beef into EAX, but main always returns hex food. It doesn't care what subroutine put into EAX. It always returns its own thing. So if you were to optimize this, for instance, if you were to compile this with optimizations, it would just straight out blank. It would get rid of all the code for sub. It would literally make main be return. Main would essentially turn into move food to EAX return, right? So in the optimized form. It wouldn't even bother calling the thing. It would say, like, I'm not going to even call it. It doesn't do anything important. Let's get rid of it. And just, in terms of calling conventions, there's no real difference here because there's no passing of parameters to the thing. There's no way that this could use, like, there could be any difference between cdecl versus standard calling conventions. So you could force this to be one way or the other, but you'd still get the same assembly code. All right, so now actually we're going to go through this sort of in the actual Visual Studio so that you can get a little bit of experience. The point here is we're going to use Visual Studio Express, which is the free version, and so the idea here is after this class, you can go take small snippets of C programs and you can put them in Visual Studio, compile them, and then walk through and debug them, see what sort of assembly is generated, see the modifications to the stack and registers, etc. So, yep, let's do this in the tool. So, you have the things in your slides which are the rough approximation of how to do it. I'm just going to walk through it anyways. So just follow along with what I'm doing on my machine. So, on your machine you should have a... oh, and for the people on the phone, I think you should all have been given some machine that you can remote desktop into in the actual lab. So there'll be something you can use here, or you can just install Visual Studio, like I said in the email, and do it yourself on your own machine. So on your machine, there will be a TPL 103 Intro x86. Does everyone have that on your desktops? I had some machines that didn't have it last time. Everyone's got that? All right. Go into the intro ASM code for class, and then open the intro to ASM.sln file, a solution file. When you do that, Visual Studio will come up. I guess it's going to initialize the environment. And so I actually don't have example 1 in here, so we're going to create example 1 just so you can see how you can go create your own projects, etc. When you want to create some things. Or you can just use Scratchpad technically, but whatever. So right-click on the solution portion and go to Add New Project. Example. All right, so you selected New Project. Go to General and select Empty Project. We're just going to call this Example 1. So General, Empty Project, Example 1, and OK. All right, now you'll get Example 1 up here at the top. Go ahead and right-click on Example 1 right away and go to Set as Startup Project. This is basically going to say whatever thing is in bold in your solution. You can have multiple projects in a single solution, and whichever one's in bold is the one that you're actually compiling at a given time. So set as startup thing, now it's bold. And then right-click on source files, go to Add, a new item. And then click on CPP file, C++ file, and we're going to do example1.c. I'm just going to call it .c so that it defaults to compiling it like C instead of C++. Shouldn't make a difference, but we'll see. So you're all adding a new C++ file, example1.c, then hit add. Now you've got example1. And I'm going to cheat and just copy it in. And you have to either go open your slides on your desktop or copy it in as well. I'll leave this up for a second so that you can write it. But write that program into your example1.c and save it. I don't know actually even if they put the slides on your desktop, so. All right. One second. Yeah, the slides aren't on your desktop actually. So you can grab them now or at break or whenever. Let's see, so I can see that one. So now we're actually going to change some of the project properties to simplify the assembly which is generated and bring it back to the kind of assembly that I just made. So the default properties of a project are going to like add sanity checks and things like that in there. So we want to get rid of those so that it'll just be the simple assembly that we just walked through. So right click on example 1 and go to properties. And now under expand the C/C++ tab, and under general, there's this debug information format one. And we want to change that to program database as opposed to program database for edit and continue. This is just saying it makes it a bit more complicated if you want it to like be able to just recompile on the fly and like change one line of source code and then it like allows it to just compile that and sticks it in for whatever you're running. So we don't want edit and continue, we just want regular debug information. So set that to program database. Next, go down to code generation. Still under C/C++. Under enable C++ exceptions, I don't think this matters at all, but I just change it anyways. So set that to no. So no C++ exceptions. Shouldn't matter, but whatever. I'm superstitious. Go to basic runtime checks and set that to default. This is basically just some sanity checks which will look for if you corrupted your stack or if you grabbed data from a variable which has not been initialized. Set that to default, which actually turns off both of those runtime checks. And then under buffer security check, this is stack cookies or stack canaries if you're aware of that. Set that to no because that'll add in extra code which adds something to the stack and then checks it to make sure you haven't buffer overflowed. So I've got to get rid of that as well. But it's good that it's on by default, right? So, okay, I think that's it from C++. Nope. Under advanced, let's see. Set this to compile as C code. So compile as C code. Again, I don't think for this super simple code that's going to matter at all, but whatever. whatever. And you can actually see here right above here, right? This is where it's setting the default calling convention to cdecl, right? And so we could actually override this and we could say everything's going to be standard call or everything's going to be fast call, which we didn't actually talk about in this class. But, you know, these are alternate places where you can force the calling convention of functions. And that's it for C++. Go to linker, and then general. And there's this thing called enable incremental linking. We want to set that to no. Because, again, that's just something where it's going to break up the code. So if we don't disable this, then when we call the function, it's not going to call directly to it. It's going to call to some jump, which then jumps to the thing. So just for simplicity's sake, we're going to get rid of that enable incremental linking. So then go ahead and hit apply and hit OK. And so now we're going to talk about how you can, let's see, did that build? Yep. All right, so when you want to actually compile this code, you can do it a couple ways. You can right-click on example 1, and then the first option there is build. And that'll just go ahead and compile it. There'll be the output down here at the bottom. It'll say, you know, 1 succeeded. So either right-click on that and hit build, or under build up here, you can build solution. That'll build everything in all those projects, or just build example 1. But I just generally right-click and hit build. Right, so that succeeded there. So we've got the stuff compiled now. We want to actually start stepping through it one assembly instruction at a time like we were just doing in the notes. So what we're going to do is first we're going to set a breakpoint. So to do that in Visual Studio, you click on the left-hand side of the C code that you want to break at. It'll create this little red bubble. And that'll say, you know, when I get to the line int main, stop there. And so just go ahead and set a break right next to int main. And then we're going to go ahead and go up to debug and start debugging, or just hit F5. So when you do that, you start debugging. You know, it'll pop up a little window in the background. If there was anything that was going to be printed out or anything like that, that would show up there, but we don't care about that for this particular code. So right now you get a little arrow in your bubble now that says I'm stopped right here at main. This now brings up your debugging interface up here at this top bar. So this little play button is continue. That says like just run the code until you hit another breakpoint or until you exit the code. This right here, break all, this is kind of like, well, this is like a pause, and this is if you have multiple threads running or something and you want to pause everyone, all the threads, just say stop wherever you are right now. Stop is just stop debugging entirely, exit the program. And this is restart, so if you've stepped too far and you want to restart and go back to the first breakpoint or something, it'll stop it, it'll debug it again, etc. This little arrow right here, sometimes if you have big code, it's not going to matter for this class, but if you have big code and you're all over the place and you don't know where you're at, you press this little arrow to get back to wherever you're currently broken at. And then these are the 3 most important things that we need to know about. So any debugger is going to have some variation on these 3 capabilities. There's step into, which says I want to go to the target of things like call instructions or jump instructions. So I want to step into the call, the function which you're calling. So for instance, if I do step into once right here, it's going to bring me to the sub instruction. And if I do step into again, now I'm going to be at the sub instruction. If I restart this and I try again, this other option is called step over. That means I don't want to like go into this function. I don't want to go into some jump thing. I want to like just execute the entire subroutine and then come back to like the next instruction in line, either the next instruction or the next C statement, something like that. So if I did step over here and then I did step over this sub, instead of the next place I'm breaking being the int sub, it's just, you know, did all of that. It went in and executed all that code, and then it stopped me after all that code was done executing. So step into and step over are very common. You're going to see those in all debuggers. And then restarting again, if I did a step into and I stepped into the subroutine, for instance, then there's frequently the option to step out of a subroutine. So you may go into a subroutine and you may decide, okay, this is boring. I don't think this matters to what I'm looking for. And so then you can do step out of the subroutine. And that just basically says continue until this would have returned and like destroyed the stack frame and executed a return instruction essentially. So, now I may be in subroutine, but if I hit the step out, it'll go ahead and step out of the subroutine and go to the next statement after that subroutine would have been completed. So we're going to see those again in GDB when we get into the Linux side of things, but step into, step out of, and step into, step over, and step out of are the three most common sort of things which every debugger should have, basically. All right, so now we've seen a little bit about stepping at the C level, right? But we want to step at the assembly level. So what we're going to do is, go ahead and debug it. Start debugging. You'll be broken at main, right? Now right-click and select Go to Disassembly. What that's going to bring up now is an intermixed view where you can see the C statements and you can see the corresponding assembly statements. So for instance, I'm broken at the beginning of main, but we know that the compiler automatically generates these 2 instructions worth of stack frame creation right at the beginning before any of the rest of, whatever you're going to do. So when the debugger breaks, it actually breaks at the first instruction of main, which happens to be, those automatic stack frame creation instructions. And then, you can see, okay, well, the C statement call subroutine looks like this actual assembly statement, call subroutine, right, and all that. So this is how you can view the assembly instructions. You can create any little C program you wanted here, compile it, break on it, and then when you're already at a breakpoint, hit Go to Disassembly, and now you can see all the rest of the assembly. So now what we need to do, for instance, is we want to show you like what the stack looks like. We want to show you where the registers are changing, things like that. But actually, I guess before that, I should point out we already have this little call stack view right here. This is what I was talking about before, where the debugger will frequently show you the call stack saying, main was actually called by __ t main crt, like C runtime startup, which was called by main C runtime startup. So the point is, there's some initialization code which happens before main is ever called, and this actually shows you where that code was. In our previous slide, we just kind of like said, somebody somewhere called main, right? That's where we care that it starts, but this will show you, and then it'll actually say, okay, well actually kernel32.dll actually executed even before that, right? And so, below that, we don't even know where, and so basically probably the kernel passed control to kernel32.dll, which is a user space DLL actually, despite being called kernel32. That's just a user space library, and so maybe the kernel passed it to that user space library, which passed it to the initialization, which passed it to your real thing. But you can't see that. You can't see the call stack back into the kernel, for instance. You only see it for user space. All right. So, anyways, let's see here. So there's a couple of things I want you to set up in terms of windows. So one, I'll just point out right here, there's this autos window. That's going to say whatever instruction, whatever registers are going to be changed by this current instruction, it's going to show you them right now. And so it automatically knows that EBP is going to be changed based on this instruction, right? So it's a push EBP. And we know that EBP, well, sorry, it's not going to be changed. Rather, it's telling you the value that's in that thing so you can see 12FFB B8 is going to be pushed onto the stack. So it'll just tell you the minimal amount of information you need to know to kind of understand what's going to happen in this current instruction. But we want to know sort of everything that's going to, all the register values. So one way we can do that is there's this watch tab right here, which everyone should have. In the watch tab, we can actually put in all of our registers. So we could just type EAX, and that's going to tell us that. And we type EBX, etc., ECX. And so we can do that, and this will tell us the values in each of those registers right now. And actually what you probably want to do then is you want to right-click and select hexadecimal display. Because we don't like looking at things in decimal, we want to be able to go bits to nibbles and stuff like that, back and forth. So when you select hexadecimal display, you'll see, okay, EAX is 00343A18, right? So this is one way that you can see it, but what I'm going to recommend instead, I mean, this is plenty fine, but there's a separate, if you go to Debug and Windows and Registers, or if you just hit Alt-5, That'll bring up a separate window that'll show all your registers all at once. So that's this window, registers window. So as you're going through, anytime a register changes on this, it'll be highlighted in red. So for instance, I'm going to execute a single instruction. I'm going to execute this push EBP. What registers do we expect are going to change based on this instruction? Matt? Yep. Did you step through it already? Yeah. So he stepped through it, so he knew, but wait, what did you say? Say that again. EBP? No, not EBP. ESP. Right. So I'm going to step over or step into, it doesn't matter for this instruction. I'm going to step over this instruction, and what I expect to be highlighted in red is EIP, because it's going to change and it's going to point at the next instruction, right? And then ESP, because I put something on the stack and the stack pointer still needs to point at the new top of the stack. So go ahead and hit step over or step into, whatever you want. Right, and we see EIP changed and ESP changed. All right, so now we can at least watch registers change, like all of the registers change all at once. So the next thing I'm going to recommend is go to Debug and Windows and then Memory, then Memory 1, or just hit Alt-6. And this is going to bring up a memory window where we can basically look at any arbitrary memory address. So I'm going to recommend you drag that window over the over to this other side. Oh, that was a fail. Hold on. I just messed up all my windows. Oh, I should have probably been, well, whatever. All right, take your tab for the memory window and drag the tab so that it gets placed, like this little highlight thing will pop up. You want it to be basically placed to the side of these other tabs, so like that. So if you grab the tab and you drag it until you see the little, that thing, says put it on the right side of your current window. Be like that. You want this little split screen view going on. So that memory window is over here and register window is over here so that you can see them both at the same time basically. So, and I'm actually going to expand my window a little bit. You're going to want to make your window a little wider so that this columns auto shows up over in your memory window. Alright, yours is fine. So yeah, it's absolutely easy to get these all messed up. So okay, you got memory and registers, that's good enough. Probably grab that right there and move it wider so that, yeah, that's good enough. And then you got registers and memory, good enough. And yeah, like that. And now grab the registers tab itself and like just drag that to like that little thing right there. There we go. Registers and memory. Catching up still? Okay. Sure. And yeah, well, yeah, never mind. I should say that the slides you have printed out for you are not going to match like the instructions exactly that I'm doing. Do you have memory and register? And yeah, you can also just pull it out and like have it be a separate window off to the side floating somewhere. But the point is we just want to be able to see memory and registers at the same time, see them both changing. All right, now we're going to change the formatting of the memory window. So right now it'll just display byte-wise memory anywhere you give it. Give it any address, that's fine. We're going to actually change this to be watching our stack change. So we're going to set the address to ESP and press return. And now it'll set that to be the address. There's this little like double green arrows in between curly brackets kind of thing right here. And if you highlight it, it'll say reevaluate automatically. You want to click on that once, and then it'll change the address back to being the symbolic ESP. All Right, so at this point, address should say ESP, and then this little reevaluate automatically double arrow thing should be clicked, and it should have sort of a box around it. And then we're going to right-click on all of this hex display of memory, and we're going to change that to 4-byte integers. So we're display it 4 bytes at a time instead of 1 byte at a time, essentially. So select that. And now we've got 4-byte things. And then under columns, I want you to set that just to 1. So now what we're going to have is this is essentially going to be our stack. Is there a question? No? Okay. All right, so this is essentially just going to be our stack. Actually, I'm going to dim the lights the rest of the way. I know that these projectors kind of suck in here, so I know it's hard to see. It's all washed out. Maybe that'll help a little bit. Alright. So yeah. Anyways, ESP set here. Click the reevaluate automatically. Columns to 1. And now what we essentially have is that's going to be our stack pointer. What? Do you not want me to turn off the lights?
No, I was just seeing what it looked like. I can't.
Oh yeah.
It looks fine.
It's just kind of washed out. It's
I
not.
just want to see if I could help it. Got it down.
That's fine. Alrighty. So hopefully everyone else has caught up by now. So now this is essentially going to be always whatever's displayed in this window will be the top of the stack, but the problem is, like I said, you have to have mental flexibility here. They're going to display low addresses high and high addresses low. So this is going to be an upside down stack from how I'm going to be drawing it. But the point here is this is the top of the stack right now. I just did a push EBP, right? I just did that instruction. And it took whatever was in EBP, which right here it says is 12FFB8, and I pushed that onto the top of the stack. So now at least, you know, if you like it better this way, at least now the top of the stack is the top, right? So I put that on the top of the stack. So now I'm going to execute the next instruction. Move ESP, which is 12FF68, into EBP. Right, so down in my little registers window, I expect the EIP to always change like every single instruction, but now what I expect to see changing is this EBP, because right now it's 12FFB8, and I'm going to put 12FF68 into it. Right? So step over, and EBP is 12FF68, and EIP changed as expected. Nothing changed on the stack. We still point at this 12FFB8 at the top of the stack at address 12FF68. All right. So now we want to step into this call instruction, right? So we want to see that the EIP gets set to 401000, right, when we do the call instruction. So we step into that. We indeed go to the first instruction of the subroutine, which is, 401000. See, EIP got set to that down there, and now ESP changed here, right? So why is ESP in red right here? Eric? No idea? So I just executed a call instruction. What's the side effect of a call instruction? You're not. You are putting the stack pointer 4 lower, but why are you putting it 4 lower? So what sort of thing does call instruction put onto the stack? It puts the address of the next instruction after the call, right? So that's how you get back from a call, is there's going to be the address of where you get back to, basically, right? So if you look at the top of your stack, you see that 401018, right? And what that is it's the address. If we go in our assembly window and we go back down here, we see, okay, well, the call address was 401013, but the address immediately after it was 401018, right? So every call instruction, it says whatever the next address is going to be, stick that onto the top of the stack, and then, go to wherever my target is. In this case, the target was 401000. And again, just to remind you to see, now I've scrolled down, I don't know where I am right now, right? Hit this little yellow arrow, and it'll bring me back up to wherever wherever my break is currently set at. So now we're in subroutine. we're going to do the common frame pointer setup, right? Got to save the previous frame pointer and then, move ESP to EBP to make our new frame pointer, right? So first thing we do is push EBP. And so go ahead and do that, step into or step over, doesn't matter for this instruction. And you do that, and then it pushes EBP onto the top of the stack, except, is my stack still correct? EBP. Yeah, I somehow messed up my stack, but whatever. Did anyone else's stack just get messed up there?
I think you clicked the unclick.
Did I? Yeah, I probably did. There you go. I accidentally unclicked the automatic update. All right, so anyways, we executed push EBP, and so what goes on the top of the stack? A copy of EBP. So EBP is 12FF68, therefore 12FF68 goes on the top of the stack. Now we're going to do the, and we saw the ESP changed, right, because we put something on the stack, so you decremented ESP by 4, right, so it was 12FF64, but now we added something onto the top of the stack, and that means you decrement by 4 12FF60, and that's why ESP is now 12FF60, because we grow towards lower addresses, right? All right, so now we're just going to move whatever's in ESP register into EBP register, and right, this is saying, wherever the top of the stack is right now, so that's what ESP is, wherever the top of the stack is pointing, I want that to be my EBP to say, like, this is where I want my new frame pointer to be, right? So, step over that, and what changes? The EBP changes, so it's saying right now EBP is always pointing at the top of my, except for this little interim, area where you're doing these two instructions, EBP is always pointing at the top of the current stack frame, right? Except for that transition. Those two instructions are basically the transition stage. By the time you get done with this instruction, the move ESP to EBP, you're back to the normal case where EBP always points at the top of the current stack frame, right? All right, so then we have moving this immediate value hex beef, but in 32, it's only displaying 16 bits of it, but it's actually moving the 32-bit value into the 32-bit EAX register. So when we execute this instruction, we expect the EAX to be updated to be hex beef, right? So EAX is now red. EIP changed as normal. And now that's all we did. Now it's time to tear down the stack frame, exit this subroutine. So we pop EBP because we haven't moved the stack at all. We haven't moved the stack frame, haven't added any local variables, nothing else. Top of the stack frame, the only thing there is the pointer to the previous stack frame. Go ahead, pop it off, right? So 12FF68, gonna pop that into the EBP register, right? Whatever's on the top. So step over it. It took that, put it into EBP register, 12FF68, and then it moved the ESP again, right? Because it's a pop instruction, it takes it off the stack, and what that means is you got to move the stack pointer so that it doesn't look like that's there anymore. So we added 4 to the stack pointer when we take something off, right? So we subtract from the stack pointer to put things on, add to the stack pointer to take things off. So now the stack pointer points to 12FF64, which looks like a saved return address to me. And so yes, we're here at the return instruction, and what does it do? It says whatever's at the top of the stack, whatever ESP is pointing right now, take that, pop it off, and put it into the EIP register, right? So popping it off means we're going to change the stack pointer, and being it's a return, we're going to change the EIP to whatever that is. And what that is right now is 401018. So the next instruction after I step over this instruction better be 401018, right? So step it. And there we are. We're back at 401018, which is, the place after the call instruction. The whole point of the call instruction, pushing the address of the next instruction is just so you can get back to it when you're done with that subroutine. So we return from the subroutine. We're sitting here ready to move hex food into EAX, and this is really just more of the same that you've already seen. You move hex food into EAX. Nothing changes on the stack. Only thing that changes is the EAX register, and then go ahead and pop the saved stack frame pointer off of the top of the stack, right? It's right here, 12FFB8. Pop that off, and then we're going to return, right? And so the one thing you can kind of see here is you can kind of thanks to the conventions that Windows is using here, you can see that the code is roughly speaking in the range 0040 something, right? And the stack is roughly in the range 0012 something, right? So when you see things on the stack, you can kind of think, either this address, if this address looks like a 12FF something, maybe it's a stack frame pointer, maybe it's just some sort of stack address, right? And if you see something that starts with 40 whatever, maybe it's just some sort of code address, right? So you can kind of keep, as a simplistic notion here, you can keep your stack addresses and code addresses kind of different because they start by different conventions which are sufficiently separated, basically. So anyways, we're going to tear down the stack frame for main, pop this saved frame pointer back into EBP, right? So execute that. 12FFB8 goes into EBP. And then we're going to execute the return instruction. It's going to take whatever's on the top of the stack, put that into EIP, add 4 to the stack pointer so that we get rid of whatever's on the top of the stack because it's like a pop. And then it's saying, execute that, and it'll say, I don't know where the source code is for where you're trying to go. Can you please tell me where the source code is? And you say, I don't know where the source code is either. I don't have the source code. But here you go. We returned out of main, and we're now in the assembly for the guy who called main, right? And so we could keep going backwards if we wanted, right? But you can see the function which called main, there was literally a call main instruction somewhere in there, right? And as far as we're concerned in this class, we don't care about the initialization and all that happens before or after main. We just care we got to main, some stuff happened, something happened before, something happened after. I don't care about that. But when you reverse engineer, this is like what you see. You see just a bunch of assembly, and you don't see something like even main. You just have to figure out, what is this in the context of everything else. So if we want to start reverse engineering the C runtime library, we can start stepping through this, but we're not going to do that for now. So as far as we're concerned, main is done. Main returned. Main had a value in EAX, food, right? And that value is still there when we return out of main. And so now if the guy who called main wants to check what it returned, which it will, it can go ahead and look at EAX. So now I'm just going to hit like play to let it continue. And you see down here it says, the program example1 native has exited with code 61453, aka hex food in hexadecimal, right? So it's saying main returned food. Fabulous. Any questions about this example, how to step through organization of your windows, things like that? We're going to, let's see, okay, it's 11:30, so we're going to, let's see what's up. I think we're going to go into the example 2. I think we have enough time. I'm going to be breaking at like 10:55 since people are going to be wanting to go to a talk here, but we're going to go into the next example and we'll get as far as we can in half an hour, 20 minutes-ish. All right, so back to the slides for a second here. You don't have to go back where you can stay in Visual Studio. We're going to go to example 2 next. But so that was our very simple thing. Our subroutine had no parameters that it took as input. All it did is call a function which returned something, and we didn't even care what the return value was. We just always returned food. So we did that in the program just to see how you can take other things and do it. And so now we're going to do the more complicated version, or not even the same version, just a different, more complicated example code, example 2. Alrighty. So now we got example 2. And again, this should be no super surprises here in terms of C stuff and trying to figure out what this is doing, right? So we got some C code. Now our C takes input, actually. C takes parameters. So it takes argc, which is, the number of arguments passed into it, like on the command line, right? So we're going to say this is a command line program. It's going to take in some command line parameters. Argc is the number of parameters. And argv is a pointer to an array of pointers, each of which points at a string. Right? So I'll show that on the board maybe here in a second. Yeah, I'll do that as well. And then, so the point is, by convention with these command line programs, the first entry of argv of 0, is going to be the name of the program itself. So in this case, like example2.exe. So So argv of 0 is going to be example2.exe. argv of 1 is going to be first parameter that you pass to it. So you do example2.exe space, 1 space blah space 3, whatever. argv of 1 would be 1 in that example because I put 1 as my first command line parameter. This main has a single local variable, a, and what it does is it uses the function a to I, which takes a string, so a implies string here, string to I integer, so it's going to take a string and turn it into an integer, a signed integer, I believe, yes. And so this a is implicitly a signed integer, right? I didn't say unsigned a, I said a, or just int a. And so it's going to say whatever the first thing is you pass in on the command line, whatever number you pass on the command line, that argv thing is actually going to be a string. It's not going to be like an actual number. It's going to be the string, ASCII character for 1, ASCII character for 0, ASCII character for 0, and then a literal 0, a null character, right? And that's how you have a string 100, right? And so a to I takes that string as input, and then it's going to turn it into the actual number 100, which you can put into a 32-bit value, right? That fits in there just fine. So it's going to turn a string into a number and store it into the A. And then it's going to call sub, and then whatever sub returns, it's going to return that, right? So it's implicitly, it's like the same thing as if you did, if you would have taken the return value from sub and put it into a variable and then done return variable, right? You can just call return and sub, and that says whatever sub returns, I'm going to return that as well, right? And so what sub is going to take, yeah, good. I think I'll have enough explaining of this that we won't get into it exactly before we break for lunch. But so what sub is going to take is one parameter is going to be argc. That's going to be the count of the number of parameters you passed in. And just for clarification, like I said, by convention, since argv of 0 is always the name of the parameter, argc is always greater than 1, right? You have at least one parameter always. It's the name of the function, the name of the executable itself. And so if I pass a parameter on the command line, argc would be 2, right? argv of 1 would be whatever I passed. So anyways, subroutine takes as its first parameter argc, whatever that happens to be, depends on how many parameters you pass in on the command line, and then a, which is the numeric form of whatever the first thing is you passed on the command line. And then sub just does some arbitrary math on it. It takes, it says, okay, well, I'm going to take the first thing and I'm going to call that variable x. I'm going to take the second thing, I'm going to call it variable y. And then I'm going to do 2 times x plus y, right? So it's just going to do some math and it's going to return whatever that calculation is. And then when it returns that, main is going to just return that as well. So this is a place where we're going to see, that value, whatever 2 times x plus y is, that's going to get put into EAX. And then it's going to return. And then before main returns, it's not going to modify EAX at all, right? It's going to just leave whatever's there so that it returns the same thing because it's doing return, the return value of the sub, right? All right, so now I just want to, for clarification purposes, because it'll definitely matter for all this assembly, I'll kind of draw a picture of how the argv and argc and stuff like that works. Bill, over to the whiteboard. All right, so I'm going to draw the stack frame for this. Let's see here. No, I want to do this. So I'm going to draw it pretty low so that we have enough room. So again, we're going to say when main starts, whoever called main pushed the parameters to main right to left onto the stack. Those parameters are the pointer to the argv, right? So it's a pointer to a pointer array, and the argc. So we know on the stack there's going to be some argv pointer and an argc. So we're going to say that main stack frame will start hereabouts, whatever. Well, okay, we're going to say this picture is going to be before we execute any instructions in main, right? So you may guess that the first instruction main is push EBP, right? We're not even going to say that the push EBP is executed right now. All we've had is the call main has executed, right? And because a call main has been called, the address of the instruction after that call instruction will be on the stack as the thing that's on the top of the stack, lowest thing on my picture right now, right? So this is going to be saved EIP of, the instruction after, I'll put this down here, but it'll be the instruction after the call of the person who called main, right? And for people, let's see, for people on the remote VTC thing, I highly recommend you draw all of the stack frames and stuff that we do, because you're going to want to go back over and make sure everything makes sense, and this thing's not in the slides and it's not anywhere else. So this is the saved EIP of the instruction after call main, right? And so before that, before it calls main, it pushes the parameters onto the stack. So right here, we would have argc. Let's see which way I'm going to put it. Argc, and I'll say that this is equal to 2, for instance. Like this will just be like the literal value 2. We're going to pretend that I'm going to execute example. We're going to pretend that I'm executing, from the command line. Example2.exe and then 100 or something like that. So this is like some command line program which we run, example2.exe 100. argc is going to be 2, and this is going to be argv of 0. This is going to be argv of 1. Right? And we'll show that when we show these things. So right here, this is going to be the other parameter passed to main. This is going to be the char star star argv. And I'll put in some fake addresses here in a second. So this thing points somewhere where there's going to be an array of pointers to strings. So what I'm going to say is, we don't care about what's in here, but this thing is going to hold the address somewhere up here on the stack, which is where typically by convention, when this stuff from command line parameters gets passed, it's going to be somewhere up higher on the stack. This argv thing is going to be pointing somewhere up here, and this is going to be argv of 0, and this is going to be argv of 1. But each of these is a character pointer. So each of these is a pointer to some string somewhere else, right? So we know that strings typically, you have a character pointer which points at some sequence of bytes which represents the string. So in reality, these are then even going to point like somewhere else farther up on the stack. This is going to point there, and this is going to point somewhere up there. And somewhere up here on the stack, I'm going to have the byte sequence like, this will be like EX AM, and then that'll be PLE2, and ... eventually terminating in a null character, right? So somewhere there's going to be a series of bytes which terminates in a null character, and this guy points at that one, and this guy points at the second one, somewhere else, somewhere much farther up on the stack. That's why I should have put less space here so I could have actually drawn it all. And so I'm going to put in real values for each of these when we go over this actual assembly code, because what you'll see is, when it accesses, argv of 0 or something like that, or argv of 1, right? In our C code, we see argv of 1 is accessed, right? So you're actually going to see it like take this value, read the value where that points to. That'll be pointing to the address of this, and then it'll do like +4 to get to argv1, and then it'll like take that pointer and it'll say push that because that's the actual pointer to the string, stuff like that. So you'll see that later, but this is the rough layout of the way that argv, argc kind of stuff works. Like this is all set up either by like the operating system or potential. I think it's still the operating system who's actually responsible for that. And then, you know, the C initialization, all that initialization code may get set up later, but this stuff is all in the stack already before even that gets called, I think. I'd have to confirm that, but I'm pretty sure from working on the Linux stuff that that's the way it works. Like the OS sets all that up, as well as environment variables are way up there and stuff like that. And then it calls the initialization, and the initialization code is responsible for pushing these two things before it calls main, but like all that's already there. So the initialization code just puts these before it calls main. All right. And like I said, I don't want to get into this before we go on break, so... Oh, good. So I have some other stuff we have to cover before we get into it. All right, a couple more instructions you're going to have to see in order to actually understand everything that's going on here. All right, so now I'm going to talk about what I'm calling the RM32 form. So I get this notion of RM32 from the Intel manuals. There's a more complicated name for it, but you know, I don't want to use that throughout because it's not as convenient. So what the RM32 form means is there's a sequence of increasingly complex ways that you can specify access to a register or memory. Like, so the single form can specify just plain register access, but if you're doing that, you don't, well, never mind. So you can access either just plain registers or memory. And so in Intel syntax, this will change later when we talk about AT&T syntax. But in Intel syntax, what you can think of is, with the exception of one instruction, which we're going to talk about next, if you ever see these angle brackets enclosing some register like this, EBX, that means you're going to memory. So it means you're going to take EBX and go to that as a memory address and pull that value from memory. So anyways, I'm getting ahead of myself. In the RM32 form, the RM32 value could just translate to a plain old register. So you could have move EBX to EAX, and there you're just taking whatever the number is in EBX, putting that number into the EAX register, right? So we go source is on this side, source is on the right, destination on the left, right? Now when we get more complex with it and we start seeing the angle brackets, what that means is, like I said, take EBX, treat it like a memory address, go to memory, read 4 bytes from memory, and put that in EAX, right? So I said we have register to memory to register forms of move instruction. So that brackets could be on one side or it could be on the other side, but it can't be on both sides because I said there's no memory to memory, right? So you'll see angle brackets on one side or the other side. So in the simple form, you know, it's just treat it like a straight up address, go there, get the memory, get the contents of memory, stick it in the register. Now it gets more complex when we add in a form like this. So we say EBX plus ECX times some constant, which can be 1, 2, 4, or 8. Treat all of the stuff inside the angle brackets as an address. So calculate whatever address that is. So if EBX is 1 and ECX is, you know, 400000, add those together, you know, and multiply that by whatever, you know, let's say X is 1 here. You know, just do the calculation for whatever's inside the angle brackets. Put it together, go to memory at that resultant address, pull it out, stick it into the register. And then it can get even more complex in that you can have that form plus another constant offset from here. But there is an actual sane reason why they're doing this. All right, so the way that they call these forms is that you have base plus index times scale plus displacement. All right, so what you can think about here is, let's say you were trying to walk through an array, for instance, right? So you've got an array of values all sequentially put into memory. So the base, in this case, may be the base of the array. You may have, you know, this EBX here. You may set that to be the base of the array. So you know my array starts here. I'm going to take the address of the start of the array, stick that into EBX. ECX now could be the index in an array, right? So you have index 0, index 1, index 2, right? But then the reason we have this X constant there is because that could be the size of the elements of the array, right? It could be an array of bytes, in which case you would want to do base plus 0 times, you know, 1, which gives you base plus 0. That's the 0th byte in a byte array. base plus 1 times 1. That gives you base plus 1. That's the index of the 1th element in a byte array. Similarly, you could have, 4-byte arrays, right? So there's 4 bytes, 4 bytes, 4 bytes. And so again, base plus 0 times 4, 0th entry. Base plus 0 times 1 times 4, right? So base plus 4, that's your 1th entry in an array, right? And therefore, you can see how that form can help you step through the elements of an array. And then this next form with the displacement, that can potentially start getting into multi-dimensional arrays, right? So remember that multi-dimensional arrays are really just array lined up after each other, right? So, well, that would maybe only help you with, well, that could help you with multi-dimensional arrays. I guess the way I explained it in the first class is more like, well, yeah, so it's multi-dimensional array. I was thinking like, let's say you have C code where you define 2 arrays in your C code, and you do like, my array 1, and you call that, say, 10 bytes, my array 2, and you call that 10 bytes. The code might, start from the base of one of them, and then index into it, sequentially, and then later on it may do like base plus displacement to get to the second array or something like that, right? So you can use the displacement to like just jump up to a second array, or you can use it for like multi-dimensional array if you have one array. It's basically any case where you would have one array right after another array, or any other reason why you'd want to just completely jump where you're sitting in memory. Yes?
Does the displacement ever get used for any of that dynamic memory location rearranging stuff whose name I don't actually properly know that you talked about before, where we're not always running it 40,000 and so forth?
So the question was like, does displacement, for instance, be used for like if the operating system decides to move around where code is going to be, for instance? And no, it wouldn't get used in that case, essentially. In those cases, like the operating system literally is just taking the data and copying it to one place or another. It really is more like if you have contiguous data and you want to like maybe offset past one array to start accessing the second array, or there's another thing. I think in like, well, theoretically using segmentation, but not really, so I won't go there. We talk about segmentation in the intermediate class, so never mind. But think of it mostly in terms of like contiguous arrays you may want to displace past one. But really, you can use it for anything. This doesn't just have to be used for array access and stuff like that. You can use it for anything. It's just that's the reason why this sort of makes sense to have base plus index times scale and then maybe a displacement, basically. Question was there? No?
I was just going to ask if that's kind of like you could use that for like an array of structures accessing the second item, but that's a multi-dimensional.
Right, exactly. An array of structures is fundamentally still just a multi-dimensional array, right? So, yep. All right, so that's the RM32 form. And this is, okay, so this is the exception to the rule that I said where you have angle brackets, you go to memory at that address. LEA is load effective address instruction. So whereas move will take the thing, go to the address and move from memory to data, to register, LEA basically just says calculate that address that's inside of the angle brackets and stick that in a register. Don't go to memory there, just stick that in a register. And so LEA is frequently used for like getting the addresses of pointers, for instance, right? So let's say instead of grabbing the value in like some array, you want to know what's the address of the value at, the 4th element of some array. You want the address. You don't want to go to memory and grab the data at that address. LEA, for instance, would be used to calculate addresses, and you don't go to memory. So this is the exception to this angle bracket rule for RM32 forms.
So in the example we're working with here, if you wanted for some reason to say exactly where example 2 started.
Right.
That's what.
Right. So potentially the question, well, the statement was, potentially in this example, we're going to work example 2 next. If you just wanted to find where the base address of example 2, where the string example 2 is, you might use LEA, but in practical purposes, since you already have that address stored in argv0, you would actually move that address out of argv0. So, but you could potentially use it that way. All right, so that's LEA. It's basically calculate an address, and then add and sub. We'll come back and go over this. I'm going to let you guys go now. We'll be back at 1 o'clock, but add and sub, it's what you think it is. It's addition and subtraction. So. All right, back at 1 o'clock. Any questions from anyone on the remote side? You know I'm going to quiz you for those of you like at the site which I am at. So it's best to ask your questions now.